Okay.
Are we okay?
Okay. So I'm going to screen demonstration. Can you see this? Yeah. Okay.
We can.
Perfect. Perfect. So I will try to show how to create code for soft core newly created. So we have CPU, and of course we want to program it. What we have at the start, we have some Ford code for our CPU. It's Ford indeed, because we have no lowest level machine code. We have Ford primitives like DAP, plus, and so on. And we want to implement some kind of these blue things. So we need compiler, we need compiled program, and we need at least two ways to use it. We want to use it as a simulator. So we can simulate our very local VHDL, and we need very low code describing content of our CPU memory. This is our first task to test is our code is even working. And maybe we need some kind of memory image to download. It depends on the way we will use our FPGA board. For example, this may be UART. It's very often to meet USB to UART converters, and it's very easy to use with any kind of terminal program. So it's usually it's not a problem to implement UART. And first step in Ford, of course, in Ford. What else? First step in Ford is to describe two memory images. This is one array to store our code, and one array to store our data, but this is not necessary. It may be for simulation. Usually data array is empty and just placeholders for variables. It's not used in real simulation because usually data memory content is initiated by Ford code. And after creating two arrays, we can describe a very simple word, placing command to first empty array cell. And briefly, what we need to implement working cross-compilator for Ford. First task is very easy. We need to describe primitive words like da, plus, and so on, so on, so on. This is very easy because every word has a corresponding CPU code. Literals it's important to know because, of course, we don't want to use a special word moving our literal from our host for compiler to our target. So what we want write, for example, 2 plus, and 2 and 2 must not be placed on the data stack on our PC. It must be converted to our CPU code. So this task is important enough, and we don't want to write, for example, 2 convert to our target CPU, when another 2 and convert to our target CPU. So this is a question we need to solve. New words, it's colon definition and semicolon. This is very easy. It's just compiling return command. So it's like a primitive word. And we also want to use variables and some kind of control structures. Okay, literals. For a long time, I use special kind of dispatch number. This is deferred word. It's a long time. This is inside but words running every time after any kind of literal is placed on the top of stack. This is a very simple approach indeed, because when I type 2, it goes to a data stack, and dispatch number is executed. By default, it's empty, so no special action is performed with number on the stack. But if I define, for example, some literal word, I can assign this word to dispatch number vector and use it every time I'm typing number for my fault CPU. In addition, I usually use can dispatch flag just for rapidly switch on and off with processing of literals. So previously we defined a very interesting approach when the high bit of command is flag for literal, and another 7 bits are going to the data stack, shifting previous number. So what we need? We need to place a seed, this line, and we need to shift remaining bit groups. So 4 bits and 7, 7, 7, 7. So our code after seed must looks like this. So this is shift, masking, and adding most significant bit, and placing command to the code array. So we must tune dispatching off to prevent processing of all literals typed here. And after this, we need to return dispatching. Okay, this is literals. Startup words. There are snippet of code, so it's starting code. We need to place code to jump forward, because at the start of our CPU will be some defining words for our program. It's not the place where our program will start. It will start at this main label. And we need to place some startup code to jump over our all vocabulary words. Okay, so this is a start definition. This is a place for our future address. So this is jump command, and this is a seed and place to for future address. Okay, I will show later. So when we execute main, we know where is it. So we're jumping forward to the address known at the main label. And end operation is very easy. It's turning dispatching numbers off and returning to fault vocabulary. So this is simple enough. Primitives are trivial. It's just to define our new words in a special some vocabulary. This is not a complete list because I just want to show how it works. Also, I want to show how works variable definition. Variable indeed is a constant in Fort, but it's not a constant in our Fort vocabulary, but it's constant in host Fort, generating literal for Fort CPU. So every time we typing, for example, variable x will be assigned to a special address and performing x, or maybe variable name, will producing literal placing on the data stack on our soft CPU. And this is it's a very simple definition of colon definition and semicolon. It's just producing return address, And you can see this switching between Ford vocabulary and Sun vocabulary. Later, I will explain why I use at least two different approaches from standard Ford. We can see it for now. Dispatch number is a very useful hook. It allows to compile letters to target CPU code. We don't need special kind of processing. We don't need special words. We just may type our Ford code as usual and perform any converting operation as needed. And I found no reasons to use N-style vocabularies. With a static structure, I use Sun vocabulary defined in Ford context, and every time I type Sun, I'm switching to set of words recovering existing definitions. So plus in Ford context will add two numbers on the stack. Plus in Sun context will produce this 48 byte for memory image of soft CPU. This is very easy. Okay, and some words about new Ford I will use to demonstrate how it works. Now I use Qt environment. I use Qt framework to write desktop application, and Qt main application just pass strings to Ford machine, define it as included header file. And what is doing Ford file is Q structures for widgets control. So there are some examples to define button and place it to application window. And I asked my daughter to draw some logo for new Ford CPU, and she answers, okay, Pushin is very cute cat, so you can use Pushin for a while preparing logo for your program. Okay, not a problem. Not a problem. Let's run it. Very easy, nothing. And this is code I just showed you. I can load it. Okay, we have button, we have pushing, and we have a very simple example, putting one to our LED port, calling pause and putting two to our LED port. Okay, okay. We can see content of our CPU memory image. Indeed, this is very low code because I'm writing it. So print code will generate strings, program will break it and will content of memory of appropriate cell. Okay. Okay. Let's copy it and let's paste it to our existing Ford CPU. Okay, and run. You can see this. We have writing to our LED port. This is our LED. This is writing signal of system bus, and now we have one in our LED. And now we have two. So our memory content is where is it? Oh, it's not a content of memory. It's just a where is program. Oops, it's because of not defined. A whole program, almost whole memory content is not defined. Yeah, this is defined cells. So we have memory array defined in our Verilog. It's initiated by our FORT program. Just write it. I can change it. I can change it. Okay. I can restart it and load script again. Okay. Memory content is refreshed. I can rerun. Oops. What happens? Oh, yeah, of course. And now we have three numbers wrote to our LID port. That's all. That's very easy. Now we have system level simulation because I don't try to simulate every part of my full CPU step by step. I'm writing FORT code. This is all the compiler. This is all the compiler indeed. I can add my comments, so you can see now it's just no operation. It's call, plus, minus, and output 22. Not too much, of course, but our CPU is very small in reality. But we have full working compiler engine, CPU engine, and we can write FORT code, process it, receive Verilog initialization file, and use it in our CID2. That's all. Thank you.
Wonderful. Incredible.
Great. Mm-hmm.
It's less than 200 lines of code.
Mm-hmm. Yeah, wonderful. Do you share the source code of this at some repository?
Oh, not yet.
Not yet. So it's
Not
in the
yet.
works.
Yes, this is very long history because I tried to use repositories, and almost every time it started from trying to rewrite it and trying to add compatibility and trying to adapt, and all my arguments was just please, let's start to sharing ideas. Let's start to understand what we need. After it, we can implement, we can use another compilers, we can use compatibility, and so on, so on, so on. Please,
Yes,
let's start with understanding idea.
I agree, Ulrich, to Ilya, and I was discussing this with Cecil. He also asked me to share my code, some of my code. And when I shared my code, I have found so much trouble because one people is with the Macintosh, the other is with the PC, the other is with Linux, the other is with Windows, the other is with Android, and the other will bring another micro or another question. So it's a word today. And if we share ideas how to do things, everybody can do that. So I agree completely.
Fair enough. Yeah, just John, I can understand this, and it's easy. And so I've been talking about the ideas.
I can say now I have about 5,000 lines of code for my Qt application. 5,000 lines of code. It's not too much to write. It's about 100 widget methods implemented. I can place buttons, check boxes. I just write. I just put console to a screen. It's incredibly easy. So it's not Ford converted to some kind of C++ application. This is C++ Qt application controlled by Ford engine.
I have a question, Ilya. My work with a virtual machine, and I already have instructions for this virtual machine. But when I have registers in the stack based CPU. My question is difficult more or complicated the CPU when you have a mixed stack based and register based CPU?
Oh, we did it about 10 years ago because it was a project combining several approaches to code generation. And well, wait, please. I will find these presentations. Yeah, have it. Please wait. Okay, I will share my screen again. I will share my screen. This is two-stage pipeline. Can you see it?
Yes.
And in registers CPU, we need to determine operands for our arithmetic logic unit. And this is complex enough two-stage multiplexing. So first, we need to multiplex all our registers to determine operand 1 and operand 2. And after this, we need to process and to calculate all possible results with two operands. This is very simple pipeline principle. So in a three-stage pipeline, we need to fetch command to decode to determine which exact registers will be used as operands and execute it. And in stack CPU, we don't need to determine by the command read it what registers will be used as operands, because it's always top two numbers on the stack. This is very easy.
Okay.
This is very easy. It is possible. It is possible, but from our experience, the clock speed of that CPU is slightly lower, because we need here we don't need to fetch operands from register file using several fields of our command, because our command will contain information about what exactly registers will be operands for the next command.
Yeah.
For the stack, it's useless. It's useless. We know operands are on the top of the stack. So
Okay.
so we don't need this part of time, T1. It's useless.
Okay. I come with this type of CPU when I work with graphics. The first version have a single word for access to register to memory to write bitmap graphics, and then I realized I wasted a register only for working with bitmap graphics, and then make 2 registers to generally traverse memory for copy or for move memory or for copy memory or for fill memory. And
so you need access to more operands on the stack.
I use 2 registers and a stack operation, and these 2 registers facilitate the memory operation because I load the address in one register and call in every word and different level this register, and when not exist in a stack.
I can say there are always reasons to use different approaches and to add register behavioral to stack CPU. Why not? Slightly lowering clock speed. This may be not a problem if you're relying on hardware acceleration. Okay. So it's always the question. Okay, clock speed and maybe minimum area and maybe minimum program. Of course, it's important, but it's always a question: are we really need this in our project? If you want to say you want to work with your graphics, for example, to your hardware accelerators connected to your CPU, of course, up to you. It's up to you. If you can write for my latest project, I'm starting with software. I'm starting with software and I'm trying to understand what exactly I want to see in my machine code. And for example, if I need 8 cells on the stack, why not? If I want to have additional special register, why not? Okay. It's always up to you. It's not because we have a brilliant font language and we must follow it step by step and not to step aside, for example. This is a very useful approach to provide behavioral you want in your program. Because it's very easy. If you want to add dedicated register, let's add it. Let's add it. If it is helpful, if you can write a working example of code that we'll use this register, it's perfect. This is 4 ways from my point of view.
I work in different contexts of you. You have a hardware and I in software, but my problem is in interpreter mode, I do graphics pixel by pixel with this approach.
Yes, I think it's very useful to use dedicated register just for graphic supporting. Okay. Of course, you can define coordinates, you can define current color. You can write numbers from the data stack to wet registers, and this is really helpful. I'm agreed, this is really helpful.
Okay.
Stack manipulation, it's not a special magic from Fort. It's just a way to organize data and provide CPU and ability to process it. If you have dedicated registers, if you have dedicated variables in your program, why not? With a special kind of mixed fault and register processing system. This is very smart approach, I think.
And now, really, what happened is when I compile to Intel to 86 assembly, I need to simulate the stack, the data stack, and the first compiler, this simulator is full in memory, but an optimizer compiler, I make a virtual stack, and try to assign registers to different cells. And when generate code, I do the better use of register in processor. But this is because I not have a stack CPU. And when you say is more simple, stack CPU, but a register CPU is more complicated in a design level of CPU.
Yes.
Okay.
This is because we have mainstream CPU design from Intel, from AMD, of course. It's the whole world must follow this way.
Okay.
This is what we have in the reality.
Pablo and Ilya, we have Bill Ratsdale. He's going to make a short presentation or short talk. And after that, we continue on the Fort Cafe. No problem.
No problem.
Bill, you are the next one.
Okay. Thank you all.